Hello dear, good morning. So how are you doing today? So we are uh, learning very exciting models of the vector machine, and we are trying to develop the model from the very basic. And in the last lecture, we developed the objective function. What was the objective? To maximize the width of the gutter. And also we have some constraint. Okay. So now when you have objective function subject to some constraint, then we are in a position to formulate the optimization problem. Let us now try to see that our objective function was objective function minimize over W half W square. So this was our objective function, and subject to yi W plus b minus 1 equal to 0. So this is my constraint, this is my objective function. Now we need to solve this problem, okay? Because W, B, nothing is known to me yet. Okay? But this is very standard problem now to solve, okay? To solve this problem, you know what we need to do. There are methods that we will follow. Lagrangian multiplier method. To solve this problem, let us use very well known method, Lagrangian multiplier method. For those this term is new, they can just get acquainted with this method. This is a very powerful method, and even if you do not know, you can just concentrate here. You may be knowing something about it. So if I have an objective function, I have constraint, then I can solve this optimization problem, okay, using Lagrangian multiplier method. Okay. For this, first step is you need to construct a Lagrangian function. Say L, which is a function of my parameter that is equals to my objective function. Okay. Minus alpha I times yi plus b minus 1. So what we have done, this is will be 6, right? So you see, using Lagrangian multiplier, so these are called Lagrangian multiplier. So what we have done, you please see, we have constructed a function L where we have taken everything, okay, the objective function, the constraint, but in front of the constraint we have multiplied it by a multiplier by parameter alpha I, which incidentally is called Lagrangian multiplier. And if you look deeply here, this is my constant, right? This equals to 0. So by multiplying it by some constant, did I do anything? No, I have just written my objective function. This is again 0. But I will achieve many things in representing through constant, through this Lagrangian multiplier, the constant equation to my objective function. I will accomplish many things because now this is a function which I can optimize. Okay? Here it is minimize. Now how to minimize? Now how to minimize L. So this is Lagrangian multiplier method. Is it clear? Means if you have so many, suppose here there is one constant, the one constant, okay, in vector form of course. If you have so many constants, so many multipliers, here corresponding to each sample there will be one constraint, and that many multipliers has to be there. Okay, Lagrangian multiplier alpha 1, alpha 2, alpha 3. If I consider say 3 support vectors, so there will be alpha 1, alpha 2, alpha 3, Lagrangian multiplier, so on and so forth. Okay, so taking this constraint which is equals to 0 multiplied by alpha and adding it to the objective function, here subtracting it doesn't matter, will give you the Lagrangian function which will reflect the objective function. So my objective function is to minimize over W this half W square, and now I have to get that objective done by minimizing L. So how to minimize L? You all of you know, again calculus method. Okay. So we will first differentiate this with respect to W. Now I am skipping that vector notations because that will for cleanliness of my expressions, but those are vectors. Okay. So I am differentiating with respect to W and making it to 0 will give me optimum W, isn't it? You see now, if I do this, then 2 is to coming here, so W equals to minus, you see, alpha constant, y constant, si. Okay, so this term will be here, huh? Alpha I, y I, and s. This is also constant, so it is 0. So this will be equal to 0. And now you see the equation is dancing. You have got optimum W value, which is our desired parameter. Okay. Very interesting, very elegant, very simple. Okay. So this is how we got optimum W. Let us take it in the form of equation 7. Now again, so please assume that for this primal problem, we are assuming that alpha are constant, okay, and L is a function of W and B. We'll relax this in solving the problem. We will discuss later. So that is 0 will give you very interesting thing. See, this is 0 minus, this is 0, now here is a B, so differentiating with respect to B, the term will be alpha sub I, y suffix I equals to 0. So this is also interesting. So alpha sub I equal to 0. Okay. So far so good. So now putting the values of W in equation 6. Equation 6. What you are getting? Okay. So let me rewrite this here. So L will be equals to half summation of alpha sub I, y suffix I, then support vector I, this is square minus alpha sub I, y suffix I is, okay, that should be mark here, but even I forget, don't worry about this because those are all vectors, they are support vectors, okay? J alpha sub j y y sub j minus alpha sub I, y suffix I times b plus alpha. Okay. So this can be now simplification. Okay. So I can write it like this. Alpha sub I, y suffix I times over j alpha sub j y sub j. So instead of square, I have expanded it like this, minus this as it is, I am writing. Later I separate it. Is there anything? No, it's correct. Okay, simplifying. So this is only simplification you have to do. Times j y suffix j suffix j. Okay, and this is what? This is from the relation of optimality you got, this is to be 0. Okay, just you see here, this is equals to 0 from 8. Okay, from 8. From 8, this is equals to, I think I should plainly write it. And this is j. So plus okay. So this is equals to, actually L equals to, again you can simplify. So this is what? Half, say this is this entire term as A. So half of A, and this is again entire term is A. Okay. So half of A minus A equals to minus half of A. So better, and this has done already. Okay, better I will bring this one to look nice. My expression, I will bring alpha I because that is plus here minus half of this alpha I y sub xi s I times over j alpha j y sub j s j. Okay, so okay, nice. Then we can further simplify it the way you want. I j alpha sub I alpha sub j y suffix I y suffix j s I dot s j, and that's the wonderful expression which you need to note down. So what we have done, you see, this is simple, right? We have just done some algebra, okay, it's class 12 level, right? So what we have done, we have written this in terms of this I suffix, and then we have, for algorithmic way of writing convenience, we have written some G. Why? Because you see, in my class, there are support vectors from both the classes, okay? So these support vectors are, say, suppose for that yi will be plus or minus 1. For this support vector yj would be plus 1. But what if I just across two classes I am doing the dot product? Okay, then I need to represent by 2 index I and j, which tells you that this is the support vector of one class, this is support vector of another class. Okay. So for writing algorithmic way only, we have introduced another, and I will just illustrate it further when I solve a problem by hand. Clearly it will be understood. Okay. So that is the thing which we have done, because now we need to write algorithm. Okay. So what is my objective? My objective is to minimize L. Objective again, you see a lot of objective is to minimize L, which is same as maximizing the dot product between the support vectors. Okay. So this is the dot product between support vectors. So it turns out that again, it was a maximization problem, maximize gutter width, and at the end, it's again happens to be that we are coming down again maximization problem. And what is the maximization problem is, because minimizing L means this is minus sign, so you have to maximize this term, and that means maximize, these are all constant for the time being assume they are constant, right? This is constant, this is constant, they are level, right? They are the Lagrangian multiplier, okay, of different class support vectors. They are the Lagrangian multiplier, and these are the two important observation you need to know. This is a so the optimization problem is coming down to a very simple maximizing the dot product between the subvectors. Okay, so if you can maximize these vectors, because these are the subvectors, so we have to figure out what are the vectors we should take so that the always always we will calculate the different subvectors, calculate the dot product, and we will take the maximum one, and that will maximize our order width. So please stay tuned and try to understand this very simple but very elegant method. We started in making a dot product between W, which is defined as a normal to the structure, to any arbitrary vector, which is representing any arbitrary sample. And we started from there, and then we introduced parameters, okay? And then step by step, we formulated the constraint, we geometrically the optimum margin concept we have introduced, the maximum margin, geometric margin, will solve our purpose. Our purpose is to design a sophisticated classifier which will always maintain a maximum distance between two classes and thereby give you better accuracy. So from that objective, it turns out that objective will be fulfilled if I can maximize the dot product between the subvectors. So I need to calculate only the dot, nothing else. Okay. So only the dot product of the subvectors I need to calculate and maximize. Whatever will be the maximum value for L, that will be corresponding. That will be corresponding to this vector. I will figure out W, and I will get B, and my design will be complete. And once the design is complete, then use the constraint again to test. So a given sample will be there. Now W, B, my machine is ready, and sample will tell, is it bigger than or less than 1 or 0? Okay. So 1 or minus 1. So this is my constraint which will actually give you everything you want. Okay. In which class sample belongs, it will be. If it is greater than 0, it definitely belongs to positive class. Or else, less than 0, it belongs to negative class, and equals to 0, which is highly unlikely, but yes, there will be equal to 0 for samples on the dot. Okay. So with this, this is called primal problem, and we have solved. We have solved the primal problem, and we would like to demonstrate how the design will work with the help of an example, concrete example. That is specifically what we do. We take a problem, small problem, which can be done by hand. So stay tuned. In the next class, we'll start from here and solve the problem to make you understand all these concepts which we have introduced here. Till then, be safe, have a nice day.